Hello everybody, welcome to my re-record of lesson 11 for solving triangles 2. Today we're going to go over the law of cosines. Before I jump in here, just a couple of things. I will not be pausing for you guys to be working on things, so you'll need to be using the pause button in this video. Go ahead and use the rewind, the fast forward. Hopefully with this being posted in YouTube, it's a little bit easier for you to like skip forward or skip backwards by 5 or 10 seconds or whatever it allows you. And that'll go a little bit smoother than the Zoom videos. So use that liberally as you listen through this video in whatever way is best for your learning. All right, let's get into it. So the law of cosines states that given a triangle with sides of lengths A, B, and C across from angles alpha, beta, and gamma respectively, then we get these three equations, which I'm going to talk through in a second. But before I do, let's just draw out some arbitrary triangle. This law of cosines works for any triangle at all. Every single triangle should work with this, as does the law of sines, by the way. And the law of cosines is sometimes referred to as a generalization of the Pythagorean theorem. So let's see, I have my triangle. If alpha goes across from A, I draw that in there. In blue, I'll have beta. Put that up at the top. The side across from that is little b. And then gamma is the obtuse angle that I've drawn here in the bottom right, and across from that is side C. And so I can really like change the order of where I put the angles as long as I keep gamma across from C, alpha across from A, and B across from beta, respectively, for these equations to work out the way they do. So the equations go like this, and they're all symmetric. They're all essentially the same thing, just changing the order of which side goes with which angle, or which side across from which angle. Let's read the equations. I have a squared equals b squared plus c squared minus 2bc times the cosine of alpha. So what I was trying to say is the a on the left side of the equal sign goes with the alpha inside the cosine on the right. And then the b squared plus c squared minus 2bc, those are the other two sides. So we see we have one of the angles is necessary here, or I need all three sides to solve for that angle. In the second equation, I have b squared equals a squared plus c squared minus 2ac times the cosine of beta. Here we see that the b squared on the left side of the equal sign corresponds to the beta inside the cosine. And then the final form is c squared equals a squared plus b squared minus 2ab times the cosine of gamma. Here we see the c squared is across on the left side of the equal sign, and the gamma is inside the cosine, so those are corresponding side across from angle. And then the other two sides, a and b, are the other terms there. So I said a second ago that this is a generalization of the Pythagorean theorem. So I'm going to take this third form and show you what I mean by that. So if I have c squared equals a squared plus b squared minus 2ab times the cosine of gamma, and say gamma was 90 degrees, so I had a right angle here. So our triangle would now change its shape a little bit. Be upright so that side A was vertical, alpha in the bottom left, side A across from it, angle beta up top with side B below, and then now gamma is 90 degrees, side C across. And so we should get c squared equals a squared plus b squared. Right? We know that that's what the Pythagorean theorem should give us if C is the hypotenuse. So if I check that in the law of cosines, I get c squared equals a squared plus b squared minus 2ab times the cosine of 90 degrees. But the cosine of 90 degrees is 0. So this does, in fact, give us the c squared equals a squared plus b squared like we would expect. So that's what I mean by this being a generalization of the Pythagorean theorem. the minus 2ab times the cosine of the angle, that's an adjustment for that angle not being quite 90 degrees. Okay, let's jump into a specific problem here and get this a little bit less abstract and just see how we're using these equations. So let's zoom in on this first one. And border here. Before I actually use the law of cosines for this problem, let's just see why we can't use the law of sines, or right? Because that's what we did last class. We said let's use the law of sines to solve these triangles, and let's take a look at what happens if I try and do that. So I would have the sine of alpha that goes across from the side length 10, so sine of alpha over 10. That would equal the sine of, looks like b goes across from 35 degrees, so 35 degrees is beta, sine of 35 degrees over b equals, and then gamma goes across from side of length 14, so sine of gamma over 14. So let's take a look at if we try and solve any of these equations. If I match the first two, sine of alpha over 10 equals sine of 35 degrees over b, we see that there's two variables, the alpha and the beta. So if I tried to isolate either, it would still have the other variable on the other side, so I couldn't get a specific value. So that's not going to be helpful for us in solving this out directly. I could take the second and third equations, set those equal to each other, but again I have two variables, the b and the gamma. So in that case I wouldn't be able to solve for either of those variables either. Finally, I could take the first and the third equation, sine of alpha over 10 equals sine of gamma over 14. Here we have alpha and gamma as two different variables, so there wouldn't be any way for us to isolate either without the other variable still being in play. So it's not going to be directly helpful for us to try and use the law of sines here. So that being the case, we're going to try and use this law of cosines in some meaningful way. So let's note how this is going to work. I've got an angle of 35 degrees, and that right away is telling me that I probably want to use the one that has that angle, that uses that angle. Okay, so if we're going to use the law of cosines, where I've kind of ruled out law of sines, it's not working here, then which of these law of cosines forms do I want to use? Well, I want to use the one, if an angle is involved here, I want to use the one that uses that angle. So that means I want to use the b squared equals a squared plus c squared minus 2ac cosine of beta, because 35 degrees is across from b. So let's plug that in. Let's just go right at it here. We've got b squared, we don't know. We're trying to find b. This equals a squared, so a is 10. So a is 10. I know that because it is across from alpha. C is 14. I know that because it's across from gamma. So I've got 10 squared plus 14 squared minus 2 times 10 times 14 times the cosine of beta is 35 degrees. Great. And this actually is really easy to solve. I just make this now, just take the square root. So b equals the square root of 100 plus 196 is the square of 14 minus 20 times 14, whatever that is, times the cosine of 35 degrees, which is not something that's on the unit circle. It's okay, I'm just going to take all of this and plug it into the calculator. And I've already done that ahead of time. So this is going to be 8.16 approximately. Cool. So now I've got side length B. Okay, from here, we could jump over to law of sines, but as a general rule, once you start with law of cosines, stick with it. This will just make the computations easier, generally speaking. If you start with law of sines, similarly, stick with law of sines through the problem. Honestly, law of cosines has a real big benefit that law of sines does not, and I'll talk about this more in a little bit, but with law of cosines, there's never an ambiguous case. There's never going to be two potential triangles. For this specific triangle, if I look at how this is set up, I take the bottom side, the angle of 35 degrees, and the side of length 10 and put those together. With those three things being fixed, there's only one triangle possible here. It's the one where we set that side B right there where it's at. So there's not going to be any ambiguity ever with any law of cosines problems. There's never going to be two potential triangles that we can get out here. So if we're using law of cosines, it's nice to just stick with it. I don't have to worry about taking a sine inverse and also using the 180 degrees minus the sine inverse part as well, like we saw last class. All right. Moving forward with this problem, we now need to find alpha and gamma. It doesn't really matter which one I go for at this point. Let's see. Let's just go with that first equation where I've got let's go for alpha. So I'm going to use the one that has alpha in it. A squared equals b squared plus c squared minus 2bc times the cosine of alpha. So plugging this stuff in, I've got 10 squared equals, this is going to be b squared. I'm just going to write b squared right now. And note that b squared is all of that up there. So we could actually take that, if we're being really precise in our calculator, we can just put all of that in parentheses and hold on to it as we go here. And that way we're not going to get any rounding errors. So 10 squared equals b squared plus c squared, that's 14 squared, minus 2 times b times c, 2 times b times 14 for c, times the cosine of alpha. So I want to solve for alpha, so I'm going to subtract the b squared and the 14 squared over. So I get 10 squared minus b squared minus 14 squared equals negative 2b. Say that's 2 times 14 is 28b times the cosine of alpha. And so dividing, I get the cosine of alpha equals 10 squared minus b squared minus 14 squared over negative 28b. And then we can plug in the 8.16 for b here and just throw this into the calculator. Or we could be real precise and use the exact values for b using the square root of 100 plus 196 minus 20 times 14 times cosine of 35 if we were in a situation where we needed to be extremely precise. Before I do that, I'm just going to note that I can move the cosine to the other side as the cosine inverse of all of this, 10 squared minus b squared minus 14 squared over negative 28b. And when I plug all of that into the calculator, we should come up with 49.38 degrees. So we're almost done here. One last thing, we still need our gamma value, but we're pretty much home free because gamma is simply going to equal 180 degrees, the total sum of the triangle's angles, minus the 35 degrees, minus the alpha angle, and plugging that all together, we should get that that is 95.62 degrees. All right, go ahead and pause the video if you need to continue taking notes on this. I'm going to go ahead and just move on forward to the next problem. I'll leave this in this frame at the moment so that we can still see the law of cosine forms above. By the way, I will give you the law of cosines on the exam. So while I really recommend generally memorizing them, I know it's really easy to forget the 2 or the negative or something like that. So I think it's a good equation to have like largely memorized, but I know that you're going to want to double check it during the exam. So I will give it to you, but don't come in blind where you don't know how to use it or anything. You need to be familiar with it, know how to use it, know how to plug the things in, and kind of halfway have it memorized already in order to use it meaningfully. All right, for part B, we're not given any angles. We haven't given them any labels, so we can really label them however we want. Just arbitrarily, I'll put alpha in the bottom, beta in the top. I don't know why I like going in this order, but I do. Maybe it's like almost like the way we play cards, always going to the left. So I don't know. For whatever reason, I have ordered it that way. It doesn't really matter as long as I make sure and note that A is 85 and B is 100 and gamma is 90, or C equals 90 because that's across from gamma. So we always just have to make sure the sides are labeled across from the angles appropriately, and then everything will work out just fine. So again, law of sines will not work here because I don't have any of the angles. Law of sines requires that we have at least one angle in order for us to get anywhere, so that we have at least one equation where there's both things known, the angle and the side. That's something that we're going to be making a big key of later. For law of sines to work, you need at least one pair of side and angle across from each other given in the problem. Cool. And we'll go into some more details of that later. I'm going to be giving, there's just going to be a list of problems that we're going to look at later in this lecture where it's like, hey, some of these work with law of sines, some work with law of cosines, some work with both. Make a decision on which one to use and when. So we'll be going over that later. I'll get into some details of that. Let's focus on law of cosines here. This is definitely a law of cosines. It doesn't really matter which one we start with. I'll rewrite a squared equals b squared plus c squared minus 2bc. These two will always match these two, times the cosine of this angle will always be the opposite, or the same as the a there. Those will always correspond. So let's plug in the information. We've got 85 squared equals b is 100 squared plus c is 90, square that, minus 2 times 100 times 90 for b and c, times the cosine of alpha. So this will allow us to get our alpha angle. So let's solve for cosine of alpha first. It's going to be 85 squared minus 100 squared minus 90 squared equals negative 2 times, well, let's say 200 here, times 90 times the cosine of alpha. And then I'll divide that over. So we've got 85 squared. These are just real big numbers. I don't think it's going to be any benefit to simplifying this at this point. We'll just plug it all into the calculator at the same time. 200 times 19, or 200 times 90 is 18 with 3 zeros after it, equals the cosine of alpha. And so alpha will equal the cosine inverse of all of that. 85 squared minus 100 squared minus 90 squared over negative 18,000. And plugging this into the calculator, we get that alpha should be approximately 72.46 degrees. At least that's what I got before. But no, that was wrong. That should be at 52.83 degrees. All right, so there's our alpha value. Sorry, I had to make a note there that was, I did a wrong answer on the solutions before. I'll be adjusting that later. So I've got alpha. Now let's go for beta. So for beta, the equation will be b squared equals a squared plus c squared minus 2ac times the cosine of beta. I hope you guys are starting to see that symmetry that I'm talking about, where it's the same equation, just rotating the letters through there. So in this case, we'll have 100 squared equals a squared is 85 squared plus c squared is 90 squared minus 2 times a is 85 times c is 90 times the cosine of beta. So I'll subtract the 85 squared and the 90 squared. So I get 100 squared minus 85 squared minus 90 squared equals negative 2 times 85 times 90 times the cosine of beta. And then I'll divide. So I get 100 squared minus 85 squared minus 90 squared divided by negative 2 times 85 times 90 equals the cosine of beta. So I take the cosine inverse of the left side to get my beta value. So cosine beta equals cosine inverse of 100 squared minus 85 squared minus 90 squared over negative 2 times 85 times 90. And when I plug that into the calculator, which I need to do here real quick, make sure as you're doing this in the calculator, you put parentheses around the numerator and denominator, and that you're in degree mode. Both of these are going to be really key to making sure the calculator knows what it's supposed to be doing here. Denominator in parentheses also, negative 2 times 85 times 90. Up, and I get 69.63 degrees. So finally I can get gamma equals 180 degrees minus alpha minus beta. So if I just use those approximate values, I get 180 minus 52.83 minus 69.63, and I get 57.54 degrees. There we go. Now I have all three angles. So I say that this triangle is solved. Now that I have all of those values. All right, let's move on to number 2. Here, we're not given the picture, so we have to draw it ourselves. Given a triangle with sides of lengths 10 and 12, adjacent to an angle of 30 degrees. I'm going to pause for a second before I finish reading it. I have an angle of 30 degrees, about like that, and sides of length 10 and 12. If that's 12, then a little shorter for 10. Give or take that. And so then let's draw this side in with this note that that's our only option, right? There's no ambiguity here. There's no potential for two triangles. With that side angle, then another side, we've locked ourselves into place. Let's make this 30 degrees the alpha, so side A is across here. And I might as well just mark in that beta's up here, so B equals 10. That means that we're putting gamma in the bottom right, so C equals 12. So we want to find the excuse me. So we want to determine the length of the missing side and the missing angles as the end to what the problem's asking us to do. So let's go straight away and find, I think that getting side A first seems pretty straightforward because we have the other two sides and we have the angle. If I use the form a squared equals b squared plus c squared minus 2bc times the cosine of alpha, I have the alpha, I have the b, and I have the c. I have all of these, so that would quickly allow me to find a. So let's plug that in. I have a squared equals, actually I'm just going to take the square root right away. So a equals the square root of, b is 10, so 10 squared is 100, plus c is 12, c squared is 144, minus 2 times b is 10, times c is 12, times the cosine of alpha is 30 degrees. And so we can just plug that into a calculator and get that A is approximately 6.01. Cool. So then we need beta or gamma. I'm going to go with beta here, just arbitrarily. And so I'll use b squared equals a squared plus c squared minus 2ac times the cosine of beta. So b squared is 100, b is 10, so b squared is 100 equals a squared. I'll plug that into the calculator, but I'm going to leave that as just a squared for now, plus c squared is 144 minus 2 times a times c is 12 times the cosine of beta. So I want to subtract the a squared and the 144 over. 100 minus 144 is negative 44, and then minus a squared equals negative 2 times 12 is 24 times a times the cosine of beta, and divide by the negative 24a to get cosine of beta equals negative 44 minus a squared over negative 24a. I am wanting to simplify that. I can cancel all the negatives here to get 44 plus a squared over 24a. So that means that beta equals the cosine inverse of 44 plus a squared over 24a, and plug that in. Should get cosine inverse of, parentheses are in the numerator, 44 plus 6.0 second, close parentheses, divide by 4 times, in parentheses, 24 times 6.01. Decimal places on there, and I get 56.26 degrees. Alright, so gamma is the last thing we need. That's 180 degrees minus 30 degrees minus beta. And so that's 180 minus 30 is 150, minus the 56.26 is 93.74 degrees. Yeah. And there we go. Now we've got all of the missing information. So we are done with this problem. right, moving on to the next page. Number 3 was really meant as practice for the class. So these are problems that I really recommend you trying first. And so like pausing the video, trying 1 or 2 of these, and then unpausing and then watching me come up with the solutions. I'm going to go through them a little bit faster without explaining quite as much as I have in the previous problems. I'll still try and give enough details that you can follow along to check your answers. So recommend that you try these first and then come back and see if you're getting the same answers as me, all right? All right, so pause the video now because I'm just going to jump right in. Here I have A, B, and C. I don't have any angles at all, so let's just try and... A and B are pretty much the same length. C is a bit longer. B is a little bit longer than A. Maybe widen that angle just a little bit. This is kind of hard to get these right, but I think that's 25, and that's 20, and that's an 18. It's not perfect, but it's not horrible. 25, as long as I have enough here to set up the problem, it's all good. B is 20, so beta is across from that. And C is, C is 25, so this should be gamma on the bottom left. And A is 18, so alpha is in the bottom right. All right. So it doesn't seem to matter which one I start with. I'll go with A squared equals B squared plus C squared minus 2BC cosine of alpha. So I've got 18 squared minus, or equals rather, equals 20 squared plus 25 squared minus 2 times 20 times 25 times the cosine of alpha. I'm going to subtract the 20 squared and the 25 squared, then divide by negative 2 times 20 times 25. So I've got 18 squared minus 20 squared minus 25 squared, and then dividing by negative 2 times 20 times 25. That all equals cosine of alpha. So alpha equals the cosine inverse of 18 squared minus 20 squared minus 25 squared, all over negative 2 times 20 times 25. And here we should get 45.49 is what I had there before. Degrees. And that does look right. All right, so now we've got alpha. Let's do beta. So B squared equals A squared plus C squared minus 2AC times the cosine of beta. So I've got then 20 squared equals 18 squared plus 25 squared minus 2 times 18 times 25 times the cosine of beta. Subtracting the 18 squared and 25 squared, I get 20 squared minus 18 squared minus 25 squared divided by negative 36 times 25 equals cosine of beta. And so I get beta equals the cosine inverse of 20 squared minus 18 squared minus 25 squared all over negative 36 times 25. And working that out in the calculator, get cosine inverse of 20 2.41 degrees. So then gamma equals 180 degrees minus alpha minus beta will work out to approximately 80 is about 82.10 degrees. Okay, for 3b, here I've got an angle and two sides, none of them match. So 25 degrees. Got here. 25 degrees. Side A, side B. 10 is the shorter, so that's B equals 10. Beta in the bottom right. Gamma up top, C is 20 on the bottom, that long side. And so let's get side length A first. So A squared equals B squared plus C squared minus 2BC times the cosine of alpha. By rewriting the formula over and over again, it just starts to ingrain in your brain. You kind of memorize it quickly, at least in your short term. What will happen is I won't teach this class or be using this for a few months, and then I'll have to re-remember it. But after using it a few times, it sticks just that much easier every single time. All right, so plugging information in, I get A equals the square root of B squared is 100 plus 400 minus 2 times 200 times the cosine of 25 degrees. Plugging that in, we get A is approximately 11.73. By the way, if you're not agreeing with any of these with your problems, shoot me an email and let me know that you're getting a different answer, and I will double check. I make mistakes too. And without you guys live checking me, then it's hard for me to know if I've made a mistake by, missing a negative or plugging something into my calculator wrong. I do that just as much as any student does. So if you're not getting the same answer as me, email me and we'll double check things to make sure, to see if maybe you're doing it right and I've made a mistake, because that's perfectly possible. All right, let's look for beta. So B squared equals A squared plus C squared minus 2AC times the cosine of beta. So I've got 100 equals A squared plus 400 minus 2 times C is 40A times the cosine of beta. Here, so cosine of beta equals 100 minus, 100 minus 400 is negative 300 minus A squared all over negative 40A. So beta equals the cosine inverse of that. It could also be that you find things in a different order than me, but your end answer should still end up the same. So it's possible of kind of just doing this in a slightly different order, right? You could have found gamma next instead of beta, and that's totally fine. So your computations will look a little bit different, but your end result should be the same. Yeah. In this case, beta works out to be approximately 21.13 degrees. That seems reasonable from the picture. And then gamma, I'm expecting to be obtuse. Gamma is 100 80 degrees minus 25 degrees minus beta, and so that should be approximately 133.87 degrees. All right, pause the video if you need to catch up. I'm going to move on here. Part C of problem 3, we've got gamma is 115 degrees, A is 18, B is 23. Again, I don't have any sides and angles matching up here. 115 degrees is a little more than 90 to be sure. So let's put 115 degrees here in the bottom left. I'll say A is 18 on the left side, and then B is 23 on the bottom. And so then the longest side across from the obtuse angle of 115 degrees, that will be side C. The top angle will be the beta, and then the bottom right angle will be alpha. Now I've drawn this. Let's go for C first. C squared equals A squared plus B squared minus 2AB times the cosine of gamma. Plugging stuff in, I get C squared equals 18 squared plus, actually I can take the square root right away for this one because I'm solving for C. C equals the square root. You guys I put a little tail on the end of my square root to say, hey, this is where it ends. It just kind of helps with the visual and keeps things from floating in and out of the square root on accident. A squared is 18 squared plus 23 squared minus 2 times 18 times 23 times the cosine of gamma is 115 degrees. A little longer here. There we go. Plug that into the calculator, and this should work out to be about 34.68. Seems reasonable. It should definitely be the longest here. All right, now we can go for alpha or beta. I'll go for alpha. So A squared equals B squared plus C squared minus 2BC times the cosine of alpha. A is 18, square that equals 23 squared plus C squared minus 2 times 23 times C times the cosine of alpha. Subtract and divide gives us cosine of alpha equals 18 squared minus 23 squared minus C squared over negative 46 times C. So alpha equals the cosine inverse of all of that. And when I plug that into the calculator, we get 28.06 degrees. Finally, we can get beta equals 180 degrees minus 115 degrees minus alpha. And plugging that into the calculator, I get 36.94 degrees. All right, let's move on to a story problem. Pretty basic example, but an example nonetheless of how this might get used. A 127-foot tower is located on a hill that is inclined at 38 degrees to the horizontal. A guy wire is to be attached to the top of the tower and anchored at a point 64 feet downhill from the base of the tower and we want to find the length of the wire that's needed in order to secure it. So we've got a hill. It's a 38-degree hill. That's a really steep hill, by the way. Here's our hill. This would be level ground right here. And that's a 38-degree angle. Let's put the tower, partway up the hill and draw a vertical tower is the assumption here. It is 127 feet tall. And we want to attach a wire 64 feet downhill. So 64 feet, it's about that right there. And so the wire is attached from the top of the tower down to the hill 64 feet downhill from the base of the tower. I'm going to call this length C. All right, so I'm going to stare at this picture. We want to find the length of C. So there's going to be a little bit of a hunt for all the information we need. The way that we look at this is I'm going to take that 38 degrees and I'm going to redraw level ground here, right? So this is the level, and that means that 38 degrees can also be written right here. That's also 38 degrees. Well, if we look closely at this, this is 90 degrees right there, right? That's a vertical tower. So off of the horizontal, it's 90 degrees, which means that this angle right here is 90 degrees minus 38 degrees is 52 degrees. So this is a little bit of a hunt, but our goal is to get over here and find this angle gamma. Now, if we're looking at the hill as a straight line, that's 180 degrees total. So gamma plus 52 degrees should add up to 180 degrees. So that tells us that gamma equals 180 minus 52 is 128 degrees. Cool. So this allows us to get that C squared equals, I have the other two sides, 64 squared plus 127 squared minus 2 times 64 times 127 times the cosine of 128 degrees. And we can take the square root of both sides, get C equals 64 squared plus 127 squared minus 2 times 64 is 128 times 127 times the cosine of 128 degrees. Close up that square root around everything. And this works out to be 173.877 feet. Cool. So that's the length of the wire needed. I'm going to make one little adjustment. We do want to state a conclusion to these story problems. Before I do, I'm going to just, I don't know, we don't say 0.877 feet very often. This 0.877 feet times 12 inches per 1 foot. To convert just the decimal part into inches, this works out to be about 10.5 inches. So we can state our conclusion using feet and inches. So the wire needs to be about 173 feet and 10.5 inches. Obviously, we would want some extra wire for tying off or however it's being secured, but that will be the length of the wire from where it's marked on the ground to the top of the tower. Awesome. All right, let's move on to page 3. So what we did in class and what I'm going to do now is we're not going to actually solve all of these triangles. So the instructions say to solve each triangle for the unknown signs and angles using the law of sines and cosines as appropriate. In other words, this is a mix of problems. Some of these require law of sines, some require law of cosines, and I'm not going to tell you which at the beginning, instead of actually solving all of them out, which would take us, a fair chunk of time here, probably another 45 minutes or so at least. We're just going to say which one, should we use law of sines or law of cosines for each of these? Is it possible to use both in any situation? And if so, which one should we choose? And then kind of come up with a general strategy for which one that we want to choose from the given information. So I like drawing pictures. I think that that's like always the strategy that I like to start with, is just draw a picture to kind of see what's going on here. If I have an angle of 113 degrees, I'll start by just drawing an angle of 113 degrees and thinking about the sides then. It looks like C matches with gamma here, so I do have a matching side and angle. So if C is 32 and B is 10, I can maybe shorten that up a little bit and say that's a length of 32 there. And then B is 10, that's the short side, so beta is up here. And can I draw that length of 32 in any other location? I suppose I could draw it out here to the left, right? But then I wouldn't be using the 113 degree angle. So it seems like that's the only possibility here. Then it looks like we must label this is alpha in the bottom right, and then A is across. So let's see if we could set something up with law of sines, see if we get anything, and then we'll see if we could set something up with law of cosines, see if there's a better option. So trying the law of sines, I'd have sine of alpha over A equals, already I see that that's not going to be very helpful there, but I get sine of beta over 10 equals, for that one I've at least got one of them, and then I've got sine of 113 degrees over 32. And this actually shows me that I could solve this for beta. So we could do this to get beta. And then from beta, I could get alpha equals beta minus, 180 degrees minus 113 degrees minus beta. Cool, so that looks like it would get us there, and then we could finally solve for A. After we have the alpha value, because that would be our last piece. Cool, so law of sines would work. If I tried law of cosines in some way, well, I'd want to use as much information as possible. I only have 3 pieces of information, so I would want to use that angle. So I'm kind of stuck using the c squared equals b squared plus, or a squared plus b squared minus 2ab cosine of 113 degrees. And if I plug all the information in, I get 32 squared equals a squared plus 10 squared minus 2 times a times 10 times the cosine of 113 degrees. And so I do, in this case, a is the only variable. So I can solve for it. However, I have an a squared and a. So we'd need to set to 0 and use the quadratic. Formula here. And that's really going to be more of a pain than just using the law of sines that we saw above. So here, either one works. But law of sines is going to be easier. All right, let's look on B. What happens here? Here I've got matching alpha and A, and then I've got B. So these are weird side lengths, and that's fine. Draw an angle of 36.6 degrees here. And let's see, level. If this is the side I don't know, it's like I'm going to do that. So if this is 36.6 degrees in red for alpha, be consistent here, 0.6 degrees. A is going to be on the opposite of that. B is 242. 0.2. Make that a little bit longer, just to give myself some room to draw. And so it's nice drawing these pictures. Now imagine you had a compass, and you stretched the compass out to be 186.2, and you put the sharp point right there at the top on that hinge. And then you drew a circle and you saw where it connected with the bottom line. Then it looks like we would get two different possibilities here, 186.2 here or here. Right? If we were drawing a circle of radius 186.2, it would sweep out and hit that bottom line in two locations. Now, this looks like it's definitely going to be a law of sines situation anytime we can get some sort of ambiguous case. Let's try them both, though, and see what happens. So I'd have sine of 36.6 degrees over 186.2 equals, label 242.2 in blue. So that's our B value. So that means we have a beta here or here. And even without drawing this picture, if you're struggling with like, how is Noah getting that picture set up? Like that's something, kind of watch and practice and try it on your own to learn it. You don't have to get it right away. It's a learning process, right? But let's look at the equations too as another strategy for determining if law of sines will work. So we don't always have to draw the picture in order to know which one will work just by seeing how the equations get set up. So we get sine of beta over 242.2 equals, and then we need gammas here, so gamma 1 and gamma 2 goes all the way across there. C1 goes here, and C2 would go all the way across. So then sine of gamma 1 or 2 would go over C, C1 or C2. And so here we can definitely find beta first, and then use that to find gamma, and then use that to find C. So the law of sines definitely works. And here we see this is an ambiguous case. If we draw law of cosine, we would get, well, I'd have to use all of the information given there. I need at least 3 things plugged in, so I need to use that angle. So I need to use a squared equals b squared plus c squared minus 2bc times the cosine of alpha. And doing that, we'd get 186.2 squared equals 242.2 squared plus c, we don't know, minus 2 times b is 186.2 times c times the cosine of 36.6 degrees. And again, this is a quadratic because there's a c squared and a c in this. So we'd need to be able to use the quadratic formula on this. And using the quadratic formula, that would give us 2 different answers for c, because we'd have that plus or minus that comes in the quadratic formula. So that can work, but it's going to be easier to use law of sines again. So sines is easier. If you feel like it, you can take on the challenge of doing it both ways and just see for yourself that law of sines really is simpler. Okay, for part C, I have 3 different sides. So I can try and draw the picture here. I do A is 10.6, and then a short side 3.5, and then I want the longest side to be 15. Something like that, right? It's not perfect by any means, but I can see the short, the medium, and the long sides. Here, for this to work, everything must be fixed, like these angles. I don't have any choice, so there's not going to be an ambiguous case. Let's get these colors in here. 10.6. B is 3.5, and C is 15.7, so we get gamma, alpha, and beta. Now, if I try law of sines, I'd have sine of alpha over 10.6 equals sine of beta over 3.5 equals sine of gamma over 15.7. And we can see here that no matter how I set up the equations, there's going to be 2 angles involved. And so law of sines does not work. And if we try law of cosines, I could really try any of them here because we have all 3 sides and none of the angles. So I'll go with a squared equals b squared plus c squared minus 2bc times the cosine of alpha. And if we plug in 10.6 squared equals 3.5 squared plus 15.7 squared minus 2 times 3.5 times 15.7 times the cosine of alpha. We see that alpha is the only thing missing here, so we could solve for it. And then we could repeat this process to find beta, and then we could do the 180 degrees minus alpha minus beta to get gamma. So law of cosines does work. Cool. All right, we've got 2 more that we're going to look at before we compare. Before we compare all of them to each other to kind of try and get the pattern of where we use which. And so moving on to here, I've got alpha and A. I have both of those, and then I have B is 28. And I'm guessing some of you are seeing the pattern already, which is awesome. If you're not, no big deal. We are going to zoom out, and I want to help kind of see how we're going to do that. So if I have a matching alpha, or a matching side and angle, then I draw the angle. Here's 70 degrees. And then I have the B is next to it is 28. And then side A is across from there. So you're going to have this. And side C, I don't know. I don't know the length of this dotted line below. That 20 is going to come down. And I mean, I'm already seeing just from this picture, I don't think there's going to be any solutions to this. If I try and draw 20 straight down, that's enough smaller than 28 that with that big angle of 70 degrees, I don't think it's going to reach. Now, it could. There's a chance that I'm wrong. Like, it could come down and reach in these two places, or it could come down and exactly reach the bottom once and make that a 90-degree angle there, where there's just a single solution. So, I mean, we should do the math and check, just to be sure. And in fact, I'll come back and do that, but I want to save that conversation for a few minutes. So if you're curious about that, don't worry, I will come back to it, promise. But let's continue just with this overarching picture right now of can we see whether we want to use law of sines or law of cosines. 8, and then there's a 20. I'm just going to pick one of these to draw right now. Let's just arbitrarily say it's here, that's a 20, and then we're not really seeing that there's any other options or that it might not work. We're not sure about that. So we see that 20 is there, and so then we have gamma up top, C on the bottom, and beta in the bottom right. And setting up the equation, we get sine of 70 degrees over 20 equals sine of beta over 28, and then sine of gamma over C. So law of sines will work. And law of cosines would require the 70-degree angle and the 20 there. So we're going to use the a squared equals b squared plus c squared minus 2bc times the cosine of alpha. Plug everything in, we get 20 squared equals 28 squared plus c squared minus 2 times 28 times c times the cosine of 70 degrees, and this uses quadratic. This is quadratic because of the c squared and the c. So use sines. Okay, so I do want to come back to that one and talk about it more, but that's definitely a sines problem. And then here I have alpha is 120 degrees, b equals 10, c equals 15. Here I don't have anything matching. I'll draw that 120 degrees first. I'll just use my black pen here. So we've got 20 degrees. And then B and C are adjacent to alpha. So 10 here. This one a little longer, so it looks like 15 for C. So A is across from there, from 120 degrees. Gamma is across from side length C equals 15. And beta is in the bottom right, is across from side length of B equals 10. So if I try law of sines, I would get sine of 120 degrees over A equals sine of beta over 10 equals sine of gamma over 15. And here we see that there's two variables in any of the equations that we pick. So sines does not work. Cosines, however, I want to use that angle, so I need to choose a squared equals b squared plus c squared minus 2bc times the cosine of 120 degrees, or of alpha, I guess. I'll do first, and then I'll plug stuff in. So we get a squared equals 10 squared plus 15 squared minus 2 times 10 times 15 times the cosine of 120 degrees. And so, yes, cosines works. Law of cosines. Cool. All right, let's zoom out and compare them all. And what's the one thing that we notice for all of them that use law of sines? So this one does not use law of sines. The one before does use law of sines. And let's key in on we're given A and alpha. For part C, law of sines did not work, and we had no matching. We didn't have A and alpha. We didn't have B and beta. We didn't have C and gamma. Right? There wasn't any matching side and angle across from each other, and we had to use law of cosines. For part B, we had A and alpha, so we had a side and angle across from each other, so we used law of sines. And again, law of cosines would work, but we'd use a quadratic, so it's not the easiest way about that. And then in part A, we had C and gamma, which is a side and angle across from each other, and so law of sines was our go-to in that case as well. So, short story. If given a corresponding corresponding, two R's, wow. Corresponding side and angle across from each other, use law of sines. Cool. All right, so that's, the main key that I want to get out of this conversation there. And then I know that arbitrary, like when could there potentially be two triangles or no triangles, something like that? When does that occur? We're going to look at B and D again in a little bit more detail. So for D first, I'm going to look at these two where I'd be solving for B. So we try this, and I set this up, I get sine of beta equals 28 times sine of 70 degrees over 20. I'm going to show this in two different ways on why we now do the following. There's going to be beta 1 equals what we would expect, just the sine inverse of everything that we just saw, 28 times sine of 70 degrees over 20. And actually, we're just going to stop here for a second. We're just going to check this value. And if we plug this in, then pause the video if you want to type this in yourself before I give it away. But this gives us no number. This is undefined. This means No triangle possible in this case. And if we go back over to the picture, like I was saying before, how this really hashes out in the image, actually, I'll leave that for the conversation we had before. What this means is that the triangle really, as we try and do it, this is 28 here. This side length C is, I mean, it doesn't matter. It's not given, and we could make it anything we want, no matter how long we make it. When this is 70 degrees, 20 won't reach all the way to the bottom when that's a 70-degree angle. So that's what's going on there. And then where we get two answers, how we'd set that up. If we don't see it in the picture, we can still find out. We can still catch this later, even if we aren't seeing it in the image right away. So for part B here, I'm going to look at this equation. So I've got sine of beta equals, move the 242.2 to the other side on top, times sine of 36.6 degrees over 186.2. Okay, so the short answer is that we'd say B1 equals sine inverse of all of this, 242.2, times sine of 36.6 degrees, all over 186.2. And when we plug this into the calculator, we'll get 59.15 degrees. So here we have at least one answer. But anytime we're in this situation where I have sine of an angle equals a number, and we're wanting that number to be between 0 and 180 degrees for a triangle, then there's also going to be B2 equals 180 degrees minus the sine inverse of, it's the same thing as before, 180 minus the one that we just did, 242.2 times sine of 36.6 degrees over 186.2. And in this case, we do 180 degrees minus the 59.15, leaves us with 120.85 degrees. And then we would check and get our gamma and make sure that everything worked out fine. There's a chance that one of these doesn't work. Like this might be too big there, but in this case, I think it will work just fine. So you then find your gamma 1 and gamma 2. But the question that I really want to address is, how do I know that this is what I need to do? Well, let's go back to just our definition of sine of an angle equals y on the unit circle. Okay. And we know that y is some positive value, and we know that the angle we're looking for, is between 0 and 180 degrees. So the unit circle theory goes, I have some angle between 0 and 180 degrees. Let's just say it's acute, and that, or let's just say that this is the y value that we're talking about, right? We know that that is, like here, this would be the y value on the unit circle, and then we're looking for the angle beta. So we would go left and right of that, and we would see that this is one answer in the first quadrant, theta 1, and this point over here, straight to the left of that y value, this would be theta 2. But theta 1 also shows up right here, and this is 180 degrees, so subtracting theta 1 from 180 degrees gets us to theta 2. So theta 2 equals 180 degrees minus theta 1. And that works in reverse also. I could say that if I took 180 degrees and subtracted theta 2, I would get theta 1. I could rearrange this equation. I would get theta, it's really theta 1 plus theta 2, adding them together equals 180 degrees. And that's why we're getting this second equation of 180 minus the sine inverse of, what I'm calling y on the unit circle. There's another way of looking at this. So, I mean, that's like the reason that I've explained before. I do want to show one other thing with this. If I'm drawing that triangle again, just kind of copy the information, and I have alpha equals 36.6 degrees, A equals 186.2, and B equals 242.2. Attempting to draw this triangle one more time. I'm going to draw an angle. It's a little shallow. Okay. A little less than 45, a tiny bit bigger than 30. So here's 36.6 degrees. I know that this is 242.2 next to it, and then put a hinge at the top, and if I'm drawing 186.2, if I took a compass at that length and swept it out and saw where it hit this baseline at these 2 points right here, let's compare this angle, this angle. Those have to be the same. This has to be an isosceles triangle right here. This is going to be the straight down. This is beta 1, and then this is also beta 1. And then we have 180 degrees across the bottom here. So beta 2 is right here. So beta 1 plus beta 2 have to add up to 180 degrees. So that means beta 2 equals 180 degrees minus beta 1, or vice versa. Vice versa. Everyone does that, right? It's vice versa, not vice. So that's the other explanation for why we have that second angle at 180 degrees minus the first angle, where the first angle is just the sine inverse of that, in this case, 242.2 times sine of 36.6 degrees divided by 186.2. Right there, right? Whew. Okay. I'd love to take questions right here and see what else you guys are interested in, but I hope that clarifies some of the conundrums that you run into in where you have an arbitrary case. It's only with law of sines where you have an angle and a side across from each other and then one other side. That's when you could potentially get it. You could also end up with a situation where you have one answer, which we saw actually in part A. Here we have an angle and the side across from it, but the angle that we're given with the side across is over 90 degrees. And what that means is that for that side across, that 32, to be on a hinge where it could be somewhere else, it would come down and not use that 113 degrees. So it's actually going to give us only one answer there. We can still set it up, but what we'll find is that the second answer will result in a negative angle somewhere, and that tells us that it's not going to work. I really, really recommend drawing pictures with all of these to kind of really connect the math, the symbolic work that you're doing with a picture, with the geometry of what's going on. That's really the fullest understanding that you can gain there, is connecting those two things. If we leave them as separate ideas and just do the equations without the pictures, or try and do the pictures, and you can't do the picture without the equation, but if we just are doing the equations without the picture, then we're not really creating as many links in our mind to understand and have a full picture of what's going on here. Remember, in the idea of learning and what is knowledge, to know something, there are a lot of different levels of knowing something. You can have a basic definition with very little connections to anything else, But the more places that you can relate that piece of information to, then we call that a higher and higher understanding. And that's true not just in math, but of understanding anything in the world. All right, we're getting close to finished, guys. And so we're going to look at number 6, do a story problem here. And then we'll prove the law of sines, prove the law of cosines, and call it a day. So let's see, moving to number 6. We have 2 planes. They leave the same airport at the same time. I'm going to read through the whole thing first. One flies at 20 degrees east of north at 500 miles an hour. And the second flies at 30 degrees east of south at 600 miles per hour. How far apart are the planes after 2 hours? So in 2 hours, I want to just kind of use that and note that that means that the first plane, it was going 500 miles an hour. So that's for 2 hours, that's 1,000 miles total. And the second plane was going 600 miles an hour, so 1,200 miles total after 2 hours. Okay, the first plane was flying 20 degrees east of north. So it's important that we are using, this is standard bearing communication that's used in airplanes and in ships. We say east of north or north of east or west of south, because I can't just say northeast. If I said 20 degrees northeast, then there can be some ambiguity, different ways of interpreting that. So this is 20 degrees north of east. And then this here, this is 20 degrees east of north. And so if I say 20 degrees northeast, then the question is, do I mean the 20 degrees east of north or 20 degrees north of east? So we always state a complete expression of which one comes first. Are we 20 degrees off of the north or 20 degrees off of the east, and in which direction? So if I'm drawing this particular problem, I want 20 degrees east of north. So I'm going to start, let's say here's the airport, and here is north, and I want it going for 1,000 miles at 20 degrees east of north. And then the second flies at 30 degrees east of south. So I'll draw in south. Let's do this. And then 30 degrees east of south is going to be a bit more out. And it's a full 1,200 miles, so it's a little bit longer here. And we want to know how far apart are the planes after 2 hours. So I want to find this length. This is the distance d, I'll say. So I need this angle in here. So that angle is going to be 180 degrees. Let's call this, I'm going to go with just theta is fine. Doesn't really matter what we name them as long as we use the formula appropriate. So theta is going to equal 180 degrees minus 20 degrees minus 30 degrees. So that's 130 degrees total. So I want to use the law of cosines that uses that angle. I don't have a side and angle across from each other in this. So I'll say d squared equals 1,000 squared plus 1,200 squared minus 2 times 1,000 times 1,200 times the cosine of 130 degrees. So d equals the square root of all of that. I definitely don't feel like working out the arithmetic as I go here. I'll plug all of these giant numbers into the calculator, let it do the thinking. And we get that this is approximately 1995.67 miles. So after 2 hours of flying, the planes are about 1995.67 miles apart. All right, hopefully that wasn't too bad there. Let's finish this up. We're finally done with all the examples here. And the last little bit of class is going to be proving the law of sines and the law of cosines. Last bit of this lecture that's recorded anyways. So to prove the law of sines, you can draw any triangle. I'm just going to get some triangle down here. And let's do this a little bit more. It really doesn't matter. I just want to make sure that this doesn't look like some sort of special triangle in any way. This is just an arbitrary triangle. I'll go ahead and label alpha here, so A is across, and then beta here, so B is across. And then I'm going to draw a vertical like this. So this is H. That height, where we have a 90-degree angle there. So from this, I know that sine of alpha equals the opposite in the right triangle is H over the hypotenuse is B. And rewriting this, I get H equals B times the sine of alpha. Similarly, I could write that the sine of beta equals the opposite here is H over the hypotenuse of this triangle now is the hypotenuse there is A, so I get H equals A sine of beta. So now I see H can be calculated in both of these ways. That allows me to put them together as B sine of alpha must equal A sine of beta. And then I can divide by A and B on both sides to get sine of alpha over A equals sine of beta over B. And then similarly, I could set up another right triangle. This one's a little bit more obscure to see. Set it up here. This would be a length H. This is gamma. This is side length C. You could say that sine of I was just going to say that we can do this by symmetry. Now I'm trying to show it. So all right, this is going to take a little bit more work. I mean, really by symmetry, this should all work out because I could have labeled these in the other way, and we get the sine of gamma over C equals these other two. But I will go ahead, since I've got this recorded. You can skip over this next part if you want, if you're okay with that explanation, or you can hang on for this. This then is 180 degrees minus gamma. So sine of 180 degrees minus gamma equals H over A. So I'm looking at the green right triangle here. And note, this is a different H. I should turn that sideways. call that H2. It's not the same one as before. Now, there's a couple of different ways of seeing this, but I think just saying there's a rotational identity that where sine of 180 degrees minus gamma is just sine of gamma. I will explain that a little bit. This does work out just fine. So if I have an angle, so I'm on my unit circle, let's draw a circle. And so I've got my y-axis, my x-axis. Let's just take, here's gamma. Then 180 degrees minus gamma is going to get us to here. And so we see the sine value for both of these is the same. It's the same y value. So here 180 degrees minus gamma gives us the same thing as just sine of gamma. So we can just simplify that down in that manner. All right, now let's look at, we'll use the sine of alpha. If I look at this big triangle here and use that alpha angle, then the sine of alpha is the opposite, is H2 over the hypotenuse for that triangle is C. And so I get H2 equals C times sine of gamma. And from this one here, I get that it equals A times the sine. Oops, sorry, that's sine of alpha there. A times sine of gamma here. This should be an alpha. I'm sorry. That's sine of alpha equals opposite is H2, hypotenuse is C. And here we can divide both sides by AC to get sine of alpha over A equals sine of gamma over C. And we already knew that sine of alpha over A equals sine of beta over B, so we can connect those, and that gives us all three equations there. Sweet. And so that's the proof of the law of sines. The law of cosines. I will again draw an arbitrary triangle. This one's a bit more algebra to get through, so hang tight. There's going to be a lot of weird factoring and whatnot. I'm going to have, feel free to pause and rewind as you need. All right, I've got to label a few things here. I'm going to call this B1 and this B2. So we're looking at the big triangle overall. I've got alpha here, and A on this side. B1 plus B2 equals B. So B equals B1 plus B2. And then C is over here on this side. So a few things happen here. I know that and I do want to label this as a height H. So using cosine, I get cosine of alpha equals the adjacent over the hypotenuse. So the adjacent is B1, the hypotenuse is C. I also know that C squared equals B1 squared plus H squared. And I also know that b squared equals b1 plus b2 squared equals b1 squared. This has to get FOILed, so we'll get a plus 2b1 times b2 plus b2 squared when that gets FOILed out all the way. All right. And then we're going to look at the other right triangle. And this is where a bunch of algebra is going to come into play here. So pause the video real quick. Make sure you're okay with all of those equations, that you see where all those are coming from. I'm going to start plugging them all together now. So I've got a squared. Got a squared equals b2 squared plus h squared. And my goal is to make this entire right side after some amount of lines equal b squared plus c squared minus 2bc times the cosine of alpha, right? That's our end goal. So I kind of want to look at this here. I see that b2 squared equals b squared minus b1 squared minus 2b1 times b2. And then h squared from this equals c squared minus b1 squared. So I'm just going to try plugging both of those in, because that gets me out of h, and it also gets me a b squared in there in that second one. So I'll have b2 squared becomes b squared minus b1 squared minus 2b1 times b2 plus h squared is c squared minus b1 squared. So that's nice. If I rearrange this a little bit, I see that I'm starting to get somewhere. I know that I want a cosine of alpha, which is b1 over c, which also tells me that b1 equals c times the cosine of alpha. That's got to be handy in some way here. So going back up to my line here, I'm just going to rearrange. Say this is b squared plus c squared. That's awesome. And I've got those. And we've got a minus b1 squared minus, or wait, there's two of those. Minus 2b1 squared minus 2b1 times b2. All right, so this next move is a little bit maybe unexpected. I mean, I worked this problem from both directions in order to get this hashed out, but I'm going to factor out a minus 2 from the left, and I'm going to factor out a b1 on the right. So that the b1 I factored out to the right, the minus 2 I factored out to the left. That left me a b1 in the first term and a b2 in the second term. And I know that b1 plus b2 is b. It's b squared plus c squared minus 2b times b1. And then just a second ago, we said that b1 equals c cosine of alpha. So I replace the b1 with c times cosine of alpha. And we're there. We've now accomplished our goal. We've shown now that a squared, on the top left there, equals b squared plus c squared minus 2 times b times c times cosine of alpha. And this was, I mean, we arbitrarily chose these names. We could rotate this around and get the other two, but we'll leave it at this. This is the proof of at least that one of those three forms. The other two forms could be proven similarly. All right, that's it. That is the lesson for the day. Thanks again for your patience in me getting this posted. I hope you all have a fantastic week, and I will talk to you in class.